Let us continue nitrogen family. In the nitrogen family, we will go for a preparation of nitrogen. About nitrogen, we will say preparation of nitrogen. Nitrogen we can prepare from atmospheric air. Atmospheric air contains nitrogen that we will take for fractional distillation. We will get a nitrogen. We will get. Next, in the laboratory, how to prepare nitrogen? We will take a ammonium chloride. Ammonium chloride salt we will take and we will add a NaNO2. Ammonium chloride salt and NaNO2 will take. We are getting what in the sense N2 we will get. We will get nitrogen gas. This double displacement we will take. What we will get means ammonium ion and NO2 minus. Therefore NH4 NO2. So let us remove all the hydrogens and oxygens by water. Remaining is what in the sense N2. Therefore 2H2O we can write plus NaCl. So ammonium chloride and NaNO2 on heating gives what in the sense nitrogen gas we can say. Then ammonium dichromate will take. Ammonium dichromate. This is heated. Ammonium dichromate on heating, it undergoes a decomposition to give N2. Here nitrogen is -3 oxidation state is converting into 0 oxidation state. This is oxidation. Chromium +6 is converting into chromium +3. That is a reduction. Chromium is undergoing reduction. So chromium is undergoing reduction. Nitrogen is undergoing oxidation. So we are getting nitrogen gas. Then azide we will take. Azide. Now we are taking barium azide. Barium azide we are taking. Azide formula is N3 minus. Barium is +2 because it is group number 2. Barium oxidation number +2 because it is coming under group number 2. Azide formula is N3 minus, we can say. Azide formula N3 minus. So barium azide, BaN3 twice we can say. This is heated. What we are getting in the sense barium and nitrogen gas we are getting. So, next sodium azide we will take. Sodium azide. This on heating what we are getting means sodium and nitrogen gas we will get. So, now this nitrogen, in this method we are getting nitrogen gas, that is very pure nitrogen gas. So azide on decomposition gives nitrogen gas, that is in very pure form. Okay. Then nitrogen gas, if you see, that is color is not there, odor is not there, taste is not there. That nitrogen is not toxic, and also nitrogen solubility in water is what in the sense very low. Solubility of nitrogen is very low in water because nitrogen is a non-polar molecule. Therefore, okay. In the nitrogen chemical reactivity, we'll see in the room temperature, nitrogen is non-reactive. Nitrogen is not going for reaction. Why nitrogen is not going for reaction in the room temperature? Because in the nitrogen, triple bond is present. To break the bond, more energy is required. Therefore, it is not going for chemical reaction easily. So, nitrogen is not going for chemical reaction at room temperature because of triple bond, high bond dissociation energy. If you add catalyst or if you raise the temperature, it will go for chemical reaction due to breaking of bond. So, what are the uses of nitrogen? We'll see. Nitrogen can be used for manufacturing ammonia in the Haber's process. It is used for preparing calcium cyanamide. Calcium cyanamide formula is CaCN2. Then this is providing inert atmosphere for many chemical reactions. During in the many chemical reactions, we will take inert atmosphere, we will take. For taking inert atmosphere, we will use nitrogen gas, we will use as a inert atmosphere. Then liquid nitrogen is used as what in the sense refrigerant. Liquid nitrogen is used as refrigerant. Okay. Next, we'll see ammonia, preparation of ammonia. Before that, calcium cyanamide formula, we will see this calcium cyanamide. Calcium cyanamide, we can write it as Ca2 plus Cn2 2 minus. Cn2 2 minus we are writing. So how to write the formula? We'll see nitrogen, carbon, nitrogen we have written. Carbon group number is 4a. Therefore, this valence shell contains 4 electrons. This -2 we will split and will give -1 to this nitrogen, -1 to this nitrogen. Nitrogen group number 5a. Therefore, this valence shell contains 5 electrons. Because of minus additional 1 electron we have given for this nitrogen also. Because of -1 we will give totally 6 electrons. Carbon makes a double bond here. Here carbon makes double bond. It is cyanamide. It is cyanamide, we can say. Cn2 2 minus. Okay. Next, we'll go for preparation of ammonia. Ammonia can be prepared by, one is manufactured by Haber's process. In the Haber's process, ammonia can be manufactured. For that, we have to give optimum conditions. We have to give. Why? Because that process is in equilibrium. That process is in equilibrium. Therefore, we have to give optimum conditions. So, what is the optimum temperature and optimum pressure? We will see. Now we will take that Haber's process equation. We'll write N2 gas plus 3H2 gas gives 2NH3 gas. It is Haber's process. We are manufacturing ammonia in this process. Here we are giving optimum temperature, how much means 700 Kelvin. Optimum pressure, we are giving how much means 200 atmosphere. Then we are taking catalyst. Catalyst is what in the sense iron oxide. Iron oxide is the catalyst, and little K2O and little Al2O3 we are taking. This is the condition we are providing in order to get high yield of ammonia. Otherwise, ammonia yield will be low because the system is at equilibrium. That's why. Okay. Then in the preparation of ammonia, other equations you will see. Then hydrolysis of urea. Urea we will take. Urea NH2, CO, NH2. This undergoes hydrolysis. This on hydrolysis, we are getting what in the sense ammonia and carbon dioxide we are getting. Ammonia and carbon dioxide. This hydrolysis reaction we'll see. Now NH2 we will take like this, and CO we will take like this. NH2 will take like this. Nitrogen can make normally 3 covalent bonds. Okay, carbon can make 4 bonds. Okay, it is urea. Now we will take water. We are taking water. We are considering water. This oxygen is having 2 lone pairs. Nitrogen is having lone pair. Now this nitrogen lone pair is attacking this hydrogen. This bond is shifting. Therefore, it becomes OH minus. Okay. So we are getting this NH2, this CO, then this CO here NH3 plus. Why NH3 plus means nitrogen is contributing lone pair to this hydrogen. Then this oxygen contributing lone pair to this carbon. This bond is shifting like this. So we can write for oxygen minus charge we will give because it is gaining the bond. Here OH will give. That in the OH minus oxygen is making bond with the carbon. Okay. For oxygen, here bond gaining, here lone pair losing. Okay. Therefore, oxygen net charge is 0. For this oxygen, we have given -1 charge because this oxygen gaining this bond. Therefore, for this nitrogen, we have given positive charge because it is losing, it is contributing lone pair. Therefore, okay. So we have got like this. Next, this O minus is will have 3 lone pairs. O minus is having 3 lone pairs. We are saying. Then this lone pair is shifting as bond pair. This bond pair shifting as lone pair. Okay. Therefore, we are getting this NH2 COOH. COOH will get NH3 detaching. Again, water is attacking. This becomes ammonia and leaving. It is what means carbonic acid, H2CO3. Okay. So again, ammonia is, again water is attacking means this is becoming ammonia and leaving. In this place, OH group comes. Therefore, it is carbonic acid. Carbonic acid is nothing but carbon dioxide and water. Okay. So urea undergoes hydrolysis to give what in the sense ammonia gas and carbon dioxide gas. Okay, urea on hydrolysis gives ammonia gas and carbon dioxide gas. We are saying. Okay, next point we will see. We will take ammonium salts. Okay, in the salt analysis, we will be given ammonium salts. Ammonium salts on heating with base, strong base. Ammonium salts on heating with a strong base, we will get ammonia vapors. Okay, whatever the ammonium salt you take ammonium salt and heat with a strong base, what vapors we will get in the sense ammonia vapors we will get ammonia gas, ammonical smell we will get, ammonia vapors we will get, that will give ammonical smell. No? So ammonium salt in the sense Suppose ammonium chloride. Ammonium chloride is the salt. Strong base in the sense we will take, suppose sodium hydroxide will take. Sodium hydroxide on heating. What happens means ammonium salt on heating with the strong base, we will get ammonia gas. That's what is there in the salt analysis. You might have done in the salt analysis. On heating ammonium salt, we will get a ammonical smell, we will get ammonia vapors, we will get. Okay, just to take ammonium salt in the test tube, add strong base and heat, you will get ammonia vapors. Okay, then what is the remaining? Sodium chloride and water. Sodium chloride and water. Okay, this sodium takes chlorine and becomes sodium chloride. Here one nitrogen is remaining, that with this OH gives water. Okay, another ammonium salt we will take. Suppose we are taking ammonium sulfate. Ammonium sulfate salt we will take, and a strong base we will add. Suppose calcium hydroxide we will add, and we will heat. So ammonium salt on heating with the base, strong base, what happens means ammonia vapors will be liberated. Ammonia vapors liberated. Calcium with the sulfate gives calcium sulfate, and this ammonium two times, therefore ammonia two times. This hydrogen with OH gives what in the sense water. Like this we will give. So ammonium salt on heating with the base, what we are getting means ammonia we are getting. Ammonium salt on heating with the base, what we will get in the sense ammonia we will get. Set. Next, preparation of ammonia we will see. Another other methods of preparation of ammonia we will see. Now we are taking what metal in the sense zinc metal we are taking. To the zinc metal, what we are adding in the sense strong base sodium hydroxide we are adding. Then to this what we are adding in the sense nitrite salt, otherwise nitrate salt we are adding. Nitrite or nitrate salt we are adding, and it is warmed, it is heated. What happens means ammonia is liberated. Ammonia gas is liberated in both cases. Nitrite is giving ammonia, nitrate also giving ammonia. Set. What is the equation? And that we'll see. Now, this zinc with sodium hydroxide, what we will get? Zinc with sodium hydroxide. Zinc with sodium hydroxide, we will get what in the sense zincate. Zincate we will get. Okay, that means we will take like this. Zinc with hydroxide. Zinc with hydroxide on heating, what happens means zinc undergoes oxidation and becomes Zn2 plus. That Zn2 plus with OH minus gives zinc hydroxide. Zinc hydroxide dissolves in excess of hydroxide to give what in the sense zincate we can say. Zincate. ZnO2 2 minus. So we are getting what means zincate we are getting. ZnO2 2 minus. Zincate we are getting. Here zinc is undergoing oxidation, hydrogen undergoing reduction, therefore we are getting hydrogen gas. Okay, we are getting hydrogen gas. So zinc on heating with a base, what happens means it is becoming salt, zincate salt, and hydrogen gas will be liberated. In this process, zinc is undergoing oxidation, hydrogen is undergoing reduction. Okay, so we got what in the sense zincate we got. This hydrogen is liberated in the form of what in the sense initially nascent hydrogen. Nascent hydrogen means newborn hydrogen. It is produced in situ. Immediately it is involving in chemical reaction. Nascent hydrogen will be produced. This nascent hydrogen we are treating with what in the sense a nitrate. Okay, nitrate with nascent hydrogen gives what in the sense NH3. NH3. Hydrogen and oxygen becomes what in the sense water. Okay. Instead of nitrate, if you take nitrite, nitrite with the nascent hydrogen also giving ammonia, we can say, then hydrogen and oxygen becomes what in the sense water. Okay, so nitrate salt gives ammonia, nitrite salt also gives ammonia, for which nascent hydrogen is required, that is provided by zinc with base on heating. So zinc on heating with a strong base gives nascent hydrogen. That nascent hydrogen reduces nitrate and nitrite into ammonia, we can say. So in this method we can, in this way we can prepare what in the sense ammonia, we can say. Ammonia we can prepare. So in the ammonium salts, if we take ammonium salts, we will take ammonium salts on heating with a strong base. What happens means ammonia gas will be liberated. Some ammonium salts will behave differently. some ammonium salts behaving differently, we are saying. One example we are taking ammonium sulfate. This ammonium sulfate on direct heating, dry heating, what happens means it decomposes to give ammonia and sulfuric acid. Ammonia and sulfuric acid vapors will be obtained. So ammonium sulfate salt on strong heating, what happens means it decomposes to give ammonia and sulfuric acid. Ammonium chloride on heating, ammonium chloride solid on heating undergoes sublimation. Ammonium chloride solid on heating undergoes what means sublimation. Okay, so ammonium sulfate on heating gives ammonia vapors, but ammonium chloride on heating undergoes sublimation, we are saying. Okay, next preparation of ammonia we'll see. We will take calcium cyanamide. We are taking calcium cyanamide. It is taken for hydrolysis. It is taken for hydrolysis. What we are getting in the sense ammonia and calcium carbonate we are getting. So what is the mechanism here? We'll see. Calcium cyanamide, we will write it as calcium ion. Cyanamide, we will write it as a cyanamide, we will write like this. Cyanamide, we are writing like this. Okay. Now it is undergoing hydrolysis to give what in the sense ammonia and calcium carbonate. It takes H plus from water. Nitrogen is a donating contributing lone pair. This bond pair is shifting. Therefore, it becomes what in similarly in this place also. So it becomes a so and so. It becomes so and so. And in water, what is the remaining means OH minus is the remaining. Okay. Next water molecule comes. Next water molecule coming. Now how the attack takes place, you see. This lone pair is contributed here. This bond pair is coming here. It is attacking here. Okay, it is attacking here. Then what happens means this bond pair is shifting here. So that what we are getting, we will see. We are getting a H, N, H, here lone pair, here C. It is having OH, here double bond, NH. Okay. In the same manner, this side also takes place. This side also takes place in the sense we will get what in the sense so and so will get so and so we are seeing. This side also taking place. Okay. Next. Again, now two OH groups attached to the same carbon in the sense it is unstable. Therefore, from this water molecule is leaving. So we are getting back what in the sense water is leaving. So we are getting a so and so. What is this in the sense urea? We got urea. This urea on hydrolysis gives ammonia, we know already. Okay, so calcium cyanamide on undergoing hydrolysis to give what substance in the sense ammonia gas, and carbonic acid will be obtained. Carbonic acid with calcium ion gives calcium carbonate. So next we will write we will take nitride. This nitride undergoes hydrolysis to give what in the sense ammonia. Nitride on undergoing hydrolysis gives ammonia. Okay, nitride with water, it takes H plus from water, and what is the remaining means in water OH minus. Therefore, we are getting a OH minus. We are getting. Okay, so nitride on hydrolysis gives ammonia. Nitride in the sense magnesium nitride, calcium nitride, lithium nitride. They are undergoing hydrolysis to give what in the sense suppose magnesium nitride undergoing hydrolysis to give ammonia and magnesium hydroxide, we can say. So these are the methods of preparing ammonia, we can say. Next, properties of ammonia. In the properties of ammonia, we are preparing ammonia. That ammonia contains water vapors. How to remove water vapors from the ammonia? How to dry the ammonia? That we'll see. Okay. So now ammonia, moist ammonia we are taking. Moist ammonia we are taking. Moist ammonia vapors we are taking. In this one, vapors we are taking. In this one, we are trying to remove water. How we are removing water in the sense we are taking a dry calcium oxide quicklime. We are taking dry quicklime. This quicklime absorbs moisture and becomes calcium hydroxide. Here, what is the remaining means ammonia vapors remaining. Okay, now moisture will not be there. So, in order to remove moisture, in order to remove moisture, what we are doing in the sense we are using quicklime we are using. So moist ammonia vapors on passing into dry quicklime, what we are getting means ammonia vapors we are getting, the moisture is absorbed by calcium oxide and becomes calcium hydroxide, we can say. Then can we use corn sulfuric acid in order to remove moisture from ammonia? No, because ammonia reacting with the sulfuric acid to give ammonium sulfate and water. So we cannot use corn sulfuric acid for drying moist ammonia, we can say. Then can we use anhydrous calcium chloride? Can we use anhydrous calcium chloride in order to dry moist ammonia? Means no. Why? Because calcium chloride makes a addition compound with ammonia. The addition compound is what in the sense so and so addition compound it makes. Calcium chloride cannot be used for drying ammonia. Why? Because calcium chloride reacts with ammonia to give a compound like this, addition compound like this, CaCl2 dot 8 NH3. Like this addition compound is obtained. Then can we use phosphorus pentoxide? Phosphorus pentoxide to dry ammonia in the sense no. Why? Because phosphorus pentoxide is acidic oxide. Ammonia is a base. Therefore, acid-base reaction possible and giving salt is ammonium phosphate like this. So how to dry ammonia? We have got an idea. Ammonia can be dried using quicklime, calcium oxide. Ammonia cannot be dried using corn sulfuric acid. We cannot use anhydrous calcium chloride. We cannot use phosphorus pentoxide to dry ammonia. Okay. Then liquor ammonia will be there in the lab. That liquor ammonia, how to open that bottle? How to open that liquor ammonia bottle? In order to take liquor ammonia, we'll see. Liquor ammonia means concentrated ammonia. How to take liquor ammonia for usage in the sense, first keep liquor ammonia bottle in the under the tap. Otherwise, keep liquor ammonia bottle in the water. In the water, keep it for some time. After some time, you open the liquor ammonia bottle and use it. Why we should do like this? Why? Because that we will see. Liquor ammonia will be filled in the dark colored bottle. Dark colored bottle, liquor ammonia will be filled. Here it is closed. First inner cap will be there and outer cap will be there. Okay, for liquor ammonia bottle. This liquor ammonia is filled up to this place and some gap will be left. Okay, liquor ammonia is filled up to this level. Some gap will be left. In this left gap, what will be there means ammonia vapors will be there. Between ammonia vapors and ammonia liquid, equilibrium will be there. In this gap, ammonia vapor is present. That ammonia vapor is exerting higher vapor pressure. Higher vapor pressure. Therefore, what we have to do means fill ammonia liquid completely. Fill ammonia liquid completely. Even then, liquor ammonia will evaporate. That vapor ammonia will be in the dissolved form here. Will be in dissolved form here. Okay. Now, this ammonia liquid can easily evaporate. Therefore, easily evaporating, therefore more volatile, therefore it has high vapor pressure. So, without cooling this liquor ammonia bottle, if you open the outer cap and inner cap, what will happen means this liquor ammonia will spit out. That means liquor ammonia will be coming out vigorous with high force because of high vapor pressure. Liquor ammonia is having high vapor pressure. Therefore, as soon as you are opening the bottle, this liquor ammonia comes out with high pressure. So what we have to do before opening this liquor ammonia bottle, cool this bottle thoroughly, cool this bottle nicely. After cooling this bottle, you open this because you are cooling in the sense vapor pressure getting reduced. Vapor pressure of liquor ammonia is getting reduced. Therefore, cool this bottle and then open. So liquor ammonia bottles, how to open, we got an idea. Otherwise, place in the ice. Liquor ammonia bottle, place in the ice. Then open it. Okay, sorry. Then next we will go for chemical properties of ammonia. chemical properties of ammonia we will see. Now we will take ammonia, we will take this ammonia vapors, we are passing over what in the sense cupric oxide. Ammonia vapors is passed over cupric oxide. What happens means copper undergoes reduction and becomes copper metal. Nitrogen undergoes oxidation and becomes a nitrogen gas. Okay. Next, this ammonia will treat with chlorine. Ammonia will treat with chlorine. This ammonia we will take excess. Ammonia will take excess. Now what happens means this hydrogen and chlorine becomes HCl. That then in this excess ammonia is reacting with this HCl and become what in the sense and become ammonium chloride. Okay, so this excess ammonia reacting with this HCl and becomes what in the sense ammonium chloride. Now this H and Cl becomes HCl, we said. Here remaining is what means N2. So N2 we are getting. Okay, so here what is the reaction we will see. We are taking NH3 excess. It is treated with chlorine. H and Cl becomes HCl and nitrogen is remaining. Then after Cl2 is exhausted, the excess ammonia react with HCl and converts HCl into ammonium chloride. Like this we can say. If we take Cl2 excess, what will happen? We'll see. NH3 with the Cl2 excess. We are taking Cl2 excess. What happens means N takes this Cl and becomes what in the sense NCl3. And H takes Cl and becomes what in the sense HCl. Okay, so we are taking in this question, in this one, we are taking in this equation, we have taken Cl2 excess. So if you take Cl2 excess, what happens means H and Cl, in the ammonia H is there, H and Cl becomes HCl. This N and Cl becomes NCl3. Okay. Then in the salt analysis, cationic analysis is there, group separation of cations. In the group separation of cations, group reagents we are using. Group 3 onwards, group 3 reagent is what in the sense ammonium hydroxide. So that means ammonia, aqueous solution of ammonia. Why we are using aqueous solution of ammonia in the group 3 cationic analysis? Means some of the metal cations will precipitate with ammonium hydroxide solution. Some of the metal cations will precipitate with ammonium hydroxide solution, further dissolves due to formation of complex with excess ammonia solution. Now we will see that one. We will see. First we will take that group separation of cations. In that that ammonia, how it is used, that we will see. Okay, so first we will take what in the sense in the group separation of cations, first group contains what cation in the sense one example Pb2 plus. Second group contains one example Cu2 plus. Third group contains one example Al3 plus. Fourth group contains one example Zn2 plus. Fifth group contains one example barium. Sixth group contains one example what in the sense ammonium. And that means magnesium will come. Magnesium. Okay, zero group contains what in the sense ammonium. Okay, like this is there. So in the group separation of cations like this, we have to do group separation of cations in salt analysis systematically. First what you have to do means take the given salt and add group 1 reagent. What is that? Means dilute HCl. If we get a precipitate, group 1 cation is present, otherwise group 1 cation is absent. So if the salt contains Pb2 plus, you will get PbCl2 white precipitate. If salt contains these cations, you will not get precipitate at all. Okay, sir. Next step. Suppose no precipitate, then what you have to do means, in the first group, how you have done in the sense you are dissolving salt in water, then you are adding dilute HCl. If you get precipitate, you can say group 1 cation is present. If precipitate is not there, you will get solution only. No, to the solution you add what in the sense H2S gas. If the salt contains Cu2 plus, then you will get CuS black precipitate. If Cu2 plus not there, then we will not get precipitate in group 2. Okay, only solution will be that take that solution and boil the solution, expel out the H2S, excess H2S. Okay, then cool the contents. Then what you have to do in the sense, go for group 3 reagent. Group 3 reagent is what in the sense ammonium hydroxide and ammonium chloride. So in the group 3 in the sense, suppose the given salt contains aluminum ion in the sense that aluminum ion is precipitating with ammonium hydroxide as aluminum hydroxide. Suppose group 4 cation is there means that group 4 cation forms precipitate with this ammonia, but that precipitate immediately dissolves in ammonia. In that way only group 5, group 6. Okay. Therefore, some of the metal cations precipitating with ammonium hydroxide, some of the metal cations precipitating with ammonium hydroxide, then further dissolves with excess of ammonium hydroxide due to formation of complex. Sir. Here, ammonium hydroxide, why can't we use in group 1? Means group 1 cation will precipitate in ammonium hydroxide. Group 2 cation also will precipitate in ammonium hydroxide. Therefore, we are not using group 1, the ammonium hydroxide in group 1, group 2. Group 3 only we are using. Okay. Sorry. So, this group 1, group 2 also precipitating with ammonium hydroxide. Sorry. So, we are not using group 1 reagent. We are using group 1 reagent as dilute HCl, group 2 reagent as H2S in acidic medium we are using. Otherwise, if you use group 3 reagent, group 1, group 2 also will precipitate. Then how to classify, how to separate? Then it is easy, not easy now. Therefore, group 1 reagent is separate, group 2 reagent is separate, group 3 reagent is separate. So shall we do this group analysis systematically, or what you see? If without doing systematically, if you directly go for group 3, what will happen? Group 1 cation also will precipitate. Then we will get wrong conclusion. Therefore, you go systematically. Okay, sir. So, which metal ions will precipitate with ammonia? That we'll see. One is zinc will precipitate with ammonia. Zinc will precipitate with ammonia as zinc hydroxide, white precipitate. Chromium will precipitate in ammonia as CrOH thrice precipitate. Ferric is precipitating in ammonia as ferric hydroxide precipitate. Ferric hydroxide precipitate. Aluminium is precipitating with ammonia as aluminum hydroxide. Okay. Then why do you say zinc is coming under group 4? Zinc is not precipitating in group 3. That's why it is going for group 4 no. Group 3 cations only will precipitate in group 3. Group 4, group 5, group 6 cations will not precipitate in group 3. But we said zinc is zinc with aqueous ammonia, zinc hydroxide, white precipitate is obtaining. We are saying. This Fe3 plus, Al3 plus and Cr3 plus coming under group 3. Group 3 cations what in the sense? Al3 plus, Fe3 plus, Cr3 plus. Group 3 cations. Okay. Fe3 plus, Al3 plus, Cr3 plus, group 3 cation. Therefore, they have precipitated with ammonia. What about zinc? Zinc is coming under group 4 only, no? It is precipitating in group 3 in the sense how zinc should come in group 4. It is placed in group 4 only. That means what we have to do, that we'll see. Now, ammonium hydroxide is dissociating to give ammonium ions and hydroxide ions. Here we have taken what in the sense aqueous solution of ammonia. Aqueous solution of ammonia. Now, in this equilibrium, hydroxide is there. This concentration is enough for precipitating zinc. Why? Because ionic product of zinc hydroxide is greater than solubility product of zinc hydroxide. Therefore, zinc is precipitating as zinc hydroxide with ammonia. That means the available concentration of hydroxide is enough for precipitating zinc. So, in this available concentration of hydroxide, ionic product of zinc hydroxide is greater than solubility product of zinc hydroxide. Therefore, zinc is precipitating. So, zinc should not precipitate in group 3. It should come under group 4. For which what we have to do? Make ionic product of zinc hydroxide less than solubility product of zinc hydroxide, then precipitation not possible. Okay. Make ionic product of zinc hydroxide less than solubility product of zinc hydroxide, then zinc will not precipitate in group 3. So we have to make ionic product less. Therefore, what you have to do? Decrease concentration of hydroxide. How to decrease concentration of hydroxide? Make backward to undergo, for which only we have added ammonium chloride. Ammonium chloride is a salt which dissociates to give ammonium ion and chloride ion. This ammonium ion is common ion here. Due to common ion effect, backward is favoring, concentration of hydroxide is reduced. Therefore, ionic product of zinc hydroxide becomes less than solubility product of zinc hydroxide. Therefore, zinc is not precipitating in group 3. So, group 4, group 5, group 7. Group 4, group 5, group 7 is not precipitating in group 3 because ionic product is less than solubility product. How we made like that means by adding ammonium chloride. So we added ammonium chloride, it gives ammonium ion, common ion. Because of common ion effect here, equilibrium favors backward, therefore concentration of hydroxide is reduced. Okay. Therefore, why group 4, group 5, group 4, group 5 and group 6 cations? Group 6 cations do not precipitate in group 3 means because of ammonium chloride giving ammonium ion, which is common ion. Because of common ion effect, OH minus concentration is reduced. The reduced concentration, that means now available concentration of OH minus is enough to precipitate group 3, but not group 4, group 5, group 6. Okay, sir. So now we can say that some of the metal ions precipitate with ammonia. Sir, next. Some of the metal ions precipitate with ammonia and dissolves in excess ammonia. Which one that is? That we will see. Now we will take copper metal ion, Cu2 plus aqueous solution will take. To this we will add ammonium hydroxide solution. This Cu2 plus takes OH minus from ammonium hydroxide solution and becomes CuOH twice precipitate. This is what precipitate in the sense blue precipitate. It is what solution in the sense blue solution. If you take copper sulfate, this intensity will be low, this intensity will be also low. To this you add ammonia. What happens? This precipitate dissolves due to formation of complex. The complex is this one. So and so complex is available. This is what in the sense deep blue solution. So copper ion is precipitating with a ammonium hydroxide solution as blue precipitate, but this precipitate dissolves in excess ammonia due to formation of complex. That complex is having deep blue color. Next, we know that silver chloride white precipitate. In the salt analysis, chloride analysis will do. Chloride analysis in the sense chloride salt with silver nitrate solution gives what in the sense AgCl white precipitate. This AgCl white precipitate with ammonia, what happens means AgCl white precipitate dissolves in ammonia due to formation of complex. It is a test for chloride, confirmatory test for chloride. Confirmatory test for chloride means we have to take chloride, we have to add silver nitrate, we will get AgCl white precipitate. AgCl white precipitate dissolves in ammonia due to formation of complex. Okay. Then we will see Uses of ammonia, we'll see. This ammonia is used for manufacturing fertilizers like urea, ammonium nitrate, ammonium sulfate, ammonium phosphate, etc. Then liquor ammonia is used as a refrigerant because heat of vaporization is high. Heat of vaporization is high. So liquor ammonia is used as a refrigerant. This liquor ammonia takes high amount of heat for vaporization. Therefore, it consumes heat from the refrigerator for vaporization. Therefore, refrigerator contents will be kept cool. It is having high heat of vaporization. Therefore, it requires more amount of heat for converting into vapor. Why? Because in liquor ammonia, between ammonia molecules, hydrogen bonding is present. Therefore, it consumes more amount of heat for vaporizing. Therefore, it is consuming heat from the refrigerator. Therefore, keeping the refrigerator cool. So, therefore, we can use liquor ammonia as a refrigerant because of high heat of vaporization. Okay, let us complete.